Welcome back, everybody, to the Algebra 2 series. Today we're looking at a neat factoring method that comes off of this particular example, and it's best illustrated here. There are other examples of it, but I just want to show you the difference between working with a difference of squares and that I rewrote this one on the right. I'll use a difference of cubes. So let's start first on the left with a difference of squares. So that would be thinking of x to the 6th as x cubed squared minus 1, or a difference of squares. If I rewrite that difference of squares in factored form, it would look like this: x cubed minus 1 and x cubed plus 1. But we know now that we have two different difference of cubes and sum of cubes. There's a difference of cubes on the left and a sum of cubes on the right, which can be factored to x minus 1 and x squared plus x plus 1. And we've seen this factorization for the first one. The second one is x plus 1 and x squared minus x plus 1. So the complete factorization looks just like this. I could box that answer, and I would be finished with it. But in the second side, if we think of this as x squared cubed minus 1, then we would rewrite this as a difference of cubes, this being my a term and 1 being the b term. So this would be x squared minus 1, and the next term would be a trinomial, x to the 4th plus x squared plus 1, if we use the difference of cubes formula. Here we see a difference of squares, which would be x minus 1 times x plus 1, and we're left with this polynomial x to the 4th plus x squared plus 1, which I did mention in class. We don't have to worry about that. It's non-factorable. But now we come to a bit of a conundrum, because we see that this is our final answer on the right, and the final answer on the left has it reduced. In other words, this trinomial must factor to these two trinomials. But how to do it? How do we factor that? So today I'm going to show you how to factor something as unique as this: x to the 4th plus x squared plus 1. In this case, in order to get that to work, we're going to have to manufacture a little something. So I'm going to take the x to the 4th and put a blank here, plus 1. And then I'm going to kind of put another blank over here. And what we're going to try to do is generate some sort of factorization principle. And in this case, I recognize that this and this can be broken into two things. So I'm going to move this minus x squared. Now you wonder why it's a minus x squared, because I'm trying to generate a difference of squares. And if that's the case, then this would have to be plus 2x squared. And I ask myself, does that work? Does that work to have that difference of squares as the entire picture? Well, notice here, this is the perfect square trinomial of x squared plus 1. So with this problem, I'm going to move this page up a bit. With this problem, I've reduced the look of this to a square of a binomial, and in the square of the binomial, I now have a difference of squares. So I'm going to rewrite the difference of squares as a factorization. So this would be, a would be over here, and b would just be the x term. So it's going to be x squared plus 1 minus x, and x squared plus 1 plus x. Or x squared minus x plus 1 and x squared plus x plus 1. So it is possible sometimes to break down something that you see when we know that it is factorable. So I would not expect us to know this. I mean, we would look at this and say, oh, I don't think I can factor that. I understand that completely. I mean, who would know that it's going to factor into these two items over here? But indeed, it does factor, and here's a nice, unique way to see that happen. Hope you enjoyed this short video.